Me veo en YouTube. Uy.
Our yes, number please. Hours. Muy bien. Bueno, pues entonces vamos a dar inicio y una pequeña introducción y luego ya vamos a empezar a ver más.
All right.
Okay, so let's see. Wait. But now let's see. Well, so the whole idea of this is to give a rough introduction to manifolds. So let me give you some background here. So let's recall first a single variable calculus, calculus 1, right? So you always have a function defined on an open interval that goes to the reals. And remember, why do we care about? Now here, why do we use an open interval? So basically, we need something open, an open interval, to take like a limit when we define a function that it is differentiable. So we need an open set. So we can approach a point from two sides. So that's why we need so we need an open space. And basically what we do here, so for instance, a continuous function. When you see this on calculus, you define a continuous function in terms of epsilon delta. So there's a limit. When you go to your course in topology, you define a function to be continuous in terms of open sets. So this is part of the things that I would like to so continuous, this is topology. Right? And this is what we will look in our setting of a manifold. So whenever we talk about derivatives in whatever sense, this is where our setting of manifolds will enter. And well, we will also see integration of manifolds, right? Okay, so that's calculus 1. And then you saw the same on multivariable calculus. So you have a function on an open set. U is open, in Rn, and you have a function 2Rm, right? And again, you studied the same concepts. Continuous, that's something that relates to topology. But in order for the function to be smooth or differentiable, that's where calculus enters, and that's what we will see on manifolds. Now, before I move on, I want to recall some things about this. So for instance, if you have a function f from u to Rm, what is the derivative or the differential of a function? How do you compute that?
With the Jacobian.
I'm sorry?
With the Jacobian.
Right,
Oh.
so you need to compute the Jacobian, and what is the Jacobian?
The matrix of all the additional derivatives in the basis.
Right, so this is something that I would like to stress. So first of all, you have the standard Euclidean coordinates, x1, xn in Rn. And then you have the component functions, f1, f2, up to fm. But that also requires that you are using the standard coordinate functions on Rn. So all of that is implicit when you define the Jacobian. So you have some coordinate, the standard coordinate system in Rn. Based on that coordinate system, f, you write it down like f1, fm, and then you do some partial derivatives, and you have a matrix, right? So in that, you use this coordinate system and also this coordinate system. So that is implicit in the Jacobian. Now, the Jacobian is a matrix, but at every point of the domain, you have a matrix. So basically, you have a family of matrices, and that will be the derivative, right? So what you have in calculus 1 so this is a 1 by 1 matrix. This is a number, but this is a 1 by 1 matrix in this setting. Okay? So based on that coordinate system, you have f1, fm coordinate functions, you take the partial derivatives, you have a matrix, and at every point of the domain on U, you have a matrix, and that will be your derivative in some sense. Okay, so that was a quick review of multivariable calculus. And now something that you also saw in multivariable calculus that you didn't cover here, but you saw it in multivariable calculus, you saw vector fields in Rn or some open subset of Rn. And maybe you also saw integral curves. I don't know if you study integral curves of vector fields. And then you have differential forms in Rn. So all of this, we will have it on manifolds. And this is what we're going to study. We're going to generalize the concepts that you have on Euclidean space. Okay, so that's the whole idea of a manifold, is to generalize the concept of an open set in Rn to something that it has a shape. It would be a sphere, or here you have the sphere. So we are going to do this, our manifolds, for instance, on this sphere, right? So this is a subset in R3, okay? So we have a subset in R3, and now as a subset, this lies in here. Is it closed, open, or none of the above?
It is close.
It's closed, right? So the two-dimensional sphere in R3 is a closed subset. So then on the sphere, you cannot use what you already know up here. Because remember that U has to be open. So you cannot talk about derivatives of functions defined on the sphere because it's not open. So that will be one of our examples of a manifold, a two-dimensional sphere. And it is a very nice example, something very natural, but is not covered on all of the knowledge that you have up to this point. Because the sphere in R3 is closed, and you only know F on open subsets of Rn. So that will be something new. A similar example, one dimension less, is the circle. The circle in R2 is also a closed set. You can define functions on the circle, but at this point, you cannot talk about if it's differentiable or not. Again, because here you're required to have an open subset, and the circle, it is closed. So these two will be examples of manifolds that we will see later on. And now on those spaces, you will be able to talk about differentiable functions, something that you cannot do at this point. Okay, so this is a very rough idea of the things that we will do. You know this, but with that knowledge, you cannot talk about differentiable functions here and here. And the two-dimensional sphere and the one-dimensional sphere, the circle, are very nice examples of geometric objects, and you would like to do calculus on them in terms of smooth functions. Okay, do you have any questions?
Nope.
Well, so we're going to start with the basic concepts of a manifold, okay? So for this, we require some knowledge of topology. point set topology to know what is a topological space and some other concepts. The whole idea is a manifold is going to be a topological space with some additional structure. But if you don't want to think in a very abstract sense, you can think of subsets of Rn, like the one that I have seen here, and those are going to be our manifolds, right? Like S2, the two-dimensional sphere, lives in R3. R3 is a topological space. You have seen the topology here. Then this has the induced topology. The same R2 is a topological space with the standard topology, the balls of radius epsilon, and then inside of R2, you have the circle. In that sense, the circle is also a topological space. It has the induced topology of R2. Is that clear? So remember, so there is some knowledge of topology here that it is required. And in some sense, it's more or less basic. So this is what I said before. This will be our topological space, abstract. If that's too much, think about it, something inside Rn. That will be your topological space. So at this point, if you have a topological space, you know and you can define continuous functions, right? If you have a function from x to the reals, you can decide if it's continuous or not continuous, because x is a topological space. However, you cannot tell if the function is differentiable or not. And I'm going to use differentiable and smooth in the same way. So the whole idea is to do something to this topological space in order to define a smooth functions. Okay, so this is going just to be a brief outline. Since X is a topological space, you can talk about an open sets. So here, I have a point X and a neighborhood of X that I call U of X. I have another point Y, and I have a neighborhood called Uy, and so on. So I have the concept of an open neighborhood. It's any open set containing that point. And then the first thing that we are going to require is I'm going to require those sets to have a function defined only on that open set. So I wrote down phi of x. This is going to be a function defined on this open neighborhood, the one that I draw here. I would like to define this function to Euclidean space. Right? This is what I have written here. And we are going to require the functions, hold on. We are going to require the function sine x to be a homeomorphism to an open set, okay? Because we have topology. So this is what we're going to require on this function. Okay, so X is a topological space. The concept of an open set makes sense, but we are going to require more. So for every point, I'm going to require that there is a neighborhood, which I call U sub X, and a homeomorphism between that open set and some open neighborhood, some open set in Rn. This I can do because remember that homeomorphism is something of topology, and here X is a topological space. Okay? So far, there is no calculus, there is only topology involved. And this is something more or less that intuitive. If you think about Earth is a two-dimensional sphere. But when you are sitting down, it is flat, right? So basically, in your home, you can see that it looks like the plane R2. So maybe Jesus is here sitting down, but locally, the floor looks flat. So it looks like R2, right? But if you go larger and larger, not only Jesus' room, but the whole city of Colima, then that's curve. Okay, so, but locally, it is flat. So this is something that we are making precise in mathematical terms. Each point has a neighborhood such that that neighborhood is homeomorphic to an open set in Rn. Okay? Here, for the meantime, this is something that it will become clear later. I have different exponents, n and m. So far, I'm not required that it is the same number. So in principle, they could be different. And this is the picture that we're going to have many, many times. So remember that phi of x is a homeomorphism between u of x and some open set. And then the other one, I have another open set. And these two, I have only topological information. They are homeomorphisms. Notice that I have a line here. Below the line, we have only topology. Okay? X is a topological space. The U's are open sets. And then I have the vertical arrows. Also, it's only topology. They are homeomorphisms. And then, in order to have something of calculus here, we are going to define calculus downstairs using your knowledge above. Here you have an open set in Euclidean space. Here you have an open space in Euclidean space. And what you have is a function here. However, that function only deals with these points in common, right? These points in common under ux go here. Under side C, go here. And that gives you a function here. And so above that line, you can talk about derivatives. And that's multivariable calculus that you have here. So that's the whole idea. Below, you cannot know nothing about derivatives. You only have topology. You go to Euclidean space. And here, you know how to take derivatives. And that information of calculus, we will use it to define calculus downstairs. That's going to be basically what we are going to do. Muy bien. Debajo de la línea es únicamente un espacio topológico, no pueden derivar. El concepto de abiertos tiene sentido. Los mapeos verticales son homeomorfismos. Todo esto sigue siendo topología. Sin embargo, arriba tienen conjuntos abiertos y en algunos casos una función, que es cuando los abiertos en X se intersectan. Estos puntos, como también están en U de X, van a dar aquí. Como también están en U de Z, van a dar acá. ¿Cómo es la intersección de los abiertos?
Abierta.
Entonces, este de acá abajo es un abierto en Rn. Acá tengo otro abierto en Rm. Y tengo una función. Tengo una función definida en un subconjunto abierto de esta manera. Phi U inversa phi b. No está definida en todo, nada más en lo que hubo en común. Esta función es continua. Phi u es un homeomorfismo, tiene una inversa y es continua. Phi z es un homeomorfismo, es continua y su inversa es continua. Así que la función de arriba es continua, inclusive tiene una inversa, la que también es continua, es un homeomorfismo. Hasta ahí no hay nada bueno. Lo interesante es de que tengo una función entre abiertos del euclidiano y ya puedo usar todo lo de cálculo de varias variables. Ya puedo derivar esa función. Entonces, el concepto que ya tenían de derivar por encima, lo vamos a trasladar para decir que podemos derivar abajo, donde no teníamos ningún concepto de diferenciación, únicamente el concepto de topología. X es un espacio topológico, abierto, funciones continuas, etc. Pero derivar para nada. Entonces lo que está arriba es lo que vamos a trasladar abajo para decir que queremos derivar. Esto es nada más una pequeña introducción de lo que vamos a estar viendo en un momento con más detalles. ¿Alguna pregunta?
Nope.
Okay, so this was just a rough outline of what we will define as a manifold and shards on a manifold. Oh, also, something that I forgot to mention, and this is very useful. So on every point, I have a neighborhood and a homeomorphism, right? You can also think about this map because it is a homeomorphism. You have a continuous map here, right? Which is defined only on some open set. In Euclidean space, you have the standard Cartesian coordinates. So you can always think of this map like giving a local parametrization of X. Okay? So if you are moving here, under this function, maybe you are moving here. If you are moving here, that means you are moving here. Right? I mean, let me make some analogy. R2, and I'm going to put X to be R2. basically this is Cartesian. And say that here you have polar coordinates. Well, I mean, no, let me put it like this. You would like to read, this is the polar coordinates. What happens when you think about it like that? So here, maybe you have r, and here you have theta, right? If you are in a point here and you move here, that means you have that, right? That's a different parameterization of R2 using polar coordinates. If you are here, so you're describing this. Las coordenadas polares es dar una parametrización distinta de R2. Entonces deben de pensar también en estos mapeos como que estamos parametrizando localmente esa parte. Siempre son las coordenadas cartesianas que tenemos arriba y de alguna manera estamos parametrizando. Y ya vieron obviamente la más sencilla parametrización de curvas y en varias variables a la mejor de superficies. Entonces, esa también va a ser una buena manera de pensar en esto. Okay, so just to finish things, think of this local, because we only have a neighborhood of x, ux. I take another point y, another neighborhood, and so on. At the end, what we would like to have are smooth functions on x. So we are going to study local things, and then there will be some condition to make this global, and then you have a smooth function on x. So from local, we will have something global. Okay, so this is just the brief outline of the things we will come now. Questions?
Nope.
So now let's make all of this more precise in our setting. So X is going to be a topological space. It's not necessarily to write it like this. I know that maybe you will write it like this, but it would not be important to stress the topology. So I will just write this, a topological space. Again, you can think X lies in Rn. X will be two-dimensional sphere or the circle. And then X is going to be called something that is locally Euclidean of dimension n if every point has a neighborhood U that is homeomorphic to an open set in Rn. This is just the precise definition of all of the things that I have defined before. Right? So this is what before I was calling ux and phi x. This is what I was using before. Sorry. UX. N. Right? Okay. Now, so again, this is the precise statement. What I was saying before with Jesus. In his house is flat, so it is locally R2. But Earth is a sphere. So I'm going to make this observation. This definition is very strong because I'm assuming it could be only locally Euclidean, but I'm stressing locally Euclidean of dimension n. And this is the observation that I would like to make. If you have two open sets in different Euclidean space, and they are homeomorphic, then n and m have to be the same. Okay? So this is a very nice statement. It requires some knowledge to prove this. ¿Han visto la demostración de esta observación?
Recuerdo haberla visto. Ahorita no recuerdo muy bien los detalles, pero
¿Perdón?
sí recuerdo haberla leído antes, pero ahorita
Ah.
no recuerdo bien los detalles. Entonces,
Okay. So I have two open sets in Euclidean space, and I put a very strong condition that they are homeomorphic. Homeomorphic, remember, means that from the point of view of topology, they are the same. The conclusion is that the ambient Euclidean space must have the same dimension. N and M are the same. One way to prove this is using algebraic topology. If you use homology, if you know homology, you can prove this. This statement is purely topological, right? I mean, I have to do things from topology, open and homeomorphic. We're going to prove this in one special case. And the proof, it relies only on topological arguments. So I'm going to assume that n is 1. Okay? So if U and V are homeomorphic and one of them lives in Rn, then they must have the same dimension. Is the statement clear? Yeah, okay. I'm going to prove this. We will use only topological arguments. U and V are open, okay? Take a point in U. Because it's open, you can put there a small interval, right? Okay? Because U is open. Now, you have a homeomorphism between U and V. Right? So let's see what happens with X naught. X naught is inside V. V is an open set in Rm. So you can put a small ball inside, okay? So you have a very small ball, open ball, epsilon in Rm. Because V is open, right? So in the same way that you can point an interval, you can put a ball. An interval in R1 is a ball, basically, right? So that's what we're using. Okay. Is this clear? Any questions up to this point? Now, now it all relies on some pictures. A, B, X naught. And here you have phi of X naught. And this is the homeomorphism, okay? Now, think about the interval A comma B. In there, you have the point X naught. If in the interval A comma B, you remove X naught, what do you get?
An open set.
Pardon?
An open set.
Yes, it will be an open set. What else?
A disconnected open set.
Right. It is disconnected. You have two disjoint open sets. So you have two components. Now, what happens on the other side? If you have a ball and you remove the center, is it going to be connected or disconnected?
Connected.
Always?
Not always. Just when the ball is equal or greater than 2.
So any ball in Rm, if you remove the center, it will always be connected for m greater or equal than 2. Only in dimension 1, if you remove the center, you will get something that is disconnected. And from topology, connectedness or non-connectedness is a topological condition. If you have a homeomorphism, If something is connected, the image will be connected, right? Because that's a topology condition under a homeomorphism. So from that, you get that M has to be equal to 1. And I mean, also this is a very basic proof, but it also shows you that you can only prove this. You cannot prove the big result. You can only distinguish between dimension 1 and the rest, but you cannot distinguish between the other dimensions. Okay? So in general, if two open sets are homeomorphic in Euclidean space, they must have the same dimension. And later in the class, we will prove this, okay? It relies on topology. We will make use of it because it is important for us. So it is the same dimension. Nice. Okay, remember, so far, we saw the definition of a topological space that it is locally Euclidean. Every point has a neighborhood and a homeomorphism to an open set in Rn. Okay, so this is again topology. In this class, we will care about smooth manifolds. And we will omit anything, we will just say manifolds. But in order to define smooth manifolds first, we have to define what is a topological manifold, right? So a topological manifold of dimension n is a topological space that it is Hausdorff, second countable, and locally Euclidean of dimension n. So that would, for us, would be a topological manifold. These two always hold when X is inside Rn with the induced topology. You will always have Hausdorff and second countable. Okay. So this is examples of topological manifolds. If you take an open set, that's going to be a topological manifold of dimension n. On Euclidean space, the induced topology will always be Hausdorff and second countable. And to check this, because X is open, you can always use the same neighborhood for any point. And the map to be the inclusion. Okay, so any open set works. For instance, in dimension 1, what are examples of topological manifolds of dimension 1, connected ones? What is an example? open sets in R1.
Like an interval?
Right, so this would be either an interval like this, or something like this, right? Now, is this homeomorphic to this one? I'm missing another one. R1 is also. So question, finite length interval, is it homeomorphic to a infinite length interval open?
Yes.
They are homeomorphic, and basically you can think about the exponential or log can give you. It requires homeomorphism. So from the topology point of view, all of these four examples are the same. They are homeomorphic. So we are missing one more example of a topological manifold of dimension 1.
Circle.
And basically these are the two examples. If you think of a curve in R2, that will be homeomorphic to an open interval a comma b. Or a curve in R3 when Rn, it will be homeomorphic to the open interval. Okay, so from the topological point of view, those are the only two examples. In higher dimensions, things get more complicated. But in one dimension, you can actually classify the topological manifolds of dimension 1. They are connected. It's either the open interval or S1, the circle. Now, I want to take X to be the union of the X-axis and the Y-axis. And is this a topological manifold of dimension 1? Basically, this is R cross R. You know that R is a one-dimensional manifold, but they have a point in common. Is X a topological manifold of dimension 1? You take a point here, and yes, that's look like an open set in R1. Yes, that's an open set in R1. What about here? A neighborhood of that point is something like this, right? X has the induced topology of R2. if you remove the origin, how many connected components will you have?
4.
4. But for an interval, if I remove an interior point, how many connected components do I get?
2. Hence, it's not a.
So any neighborhood of this point cannot be homeomorphic to an open interval. So this is not a topological manifold of dimension 1, okay? And the only trouble is the origin. Because locally, it doesn't look like an interval, an open interval of R1. Now, the third example is this one. Same question. Is this a topological manifold of dimension 1?
Yes.
So here, there's no problem. This neighborhood, you can find a homeomorphism to an open interval. So it looks like that's the only point when you have to think about it for a while, but it's no problem. Okay, so this is a topological manifold of dimension 1, right? Okay. So far we have seen only topology, and let's move on to have the concept of a manifold. So I'm going to define a concept which we haven't before, but now I'm going to make them more precise. A shard. This is the same thing that we had before, I just put it a name. A shard about a point X is a neighborhood of X and a homeomorphism to Euclidean space. Okay? So there's nothing new. I'm just putting a name, something that we had before. And remember, from now on, X is going to be a topological space, second countable, Hausdorff, and locally Euclidean. So I'm putting a name to this. This is something optional. Sometimes we will use it, sometimes it will not be important. It's just like a normalization condition. X goes to the origin. Sometimes it will be convenient to have that assumption on the chart. So this is what before, when I was motivating all of the concepts. So that's the name of a chart. A neighborhood and a homeomorphism. En español esto se llama carta. Y les digo, todo lo que vimos al inicio de motivación, ahora lo vamos a formalizar. Esta es una carta y nada más quiero que vean porque de dónde viene el nombre de carta.
Carta de navegación.
Exactamente, tiene que ver con eso, ¿de acuerdo? Entonces, tiene que ver con la navegación, tal cual. Entonces, carta viene de ahí, es una carta, porque es algo local. Información local. Ok, esto en ocasiones es importante y otras no. Nada más normalizamos esa condición. Okay, so I have a chart about a point X. So now, if I have two charts that overlap, this is what I told you before, that you have these functions, right? So remember, U is open, V is open. Let's assume that U and V intersect. That means that this is an open set of U and an open set of V. Under the homomorphism, this is mapped to an open set here. This is mapped to this open set. And so now I have a function. Now, note that I'm using the same dimension because they overlap. So this is the observation that we discussed before. This open set is homeomorphic to this one under this map. So the dimensions must be the same. So that's why now I'm using the same n, right? And this function is only defined here. And that function is a homeomorphism between that open set and this open set. So I go here under 5u inverse, and then I go up under 5v. And here is the same, equivalent. From this, I go down under 5v inverse, and then I go up under 5u. So every time that I have two charts, either they don't overlap, which I don't care, but if they overlap, I have this info. And that is going to give me the next definition of a compatible charts. So I have two charts, U and V, on X, and I'm going to say that they are compatible if this function and this function are C infinity functions or smooth functions. If U and V don't overlap, I will assume also that they are compatible. U and V are compatible if they don't intersect, and if they intersect, these two functions must be C infinity. So here is where you are using the knowledge of multivariable calculus. Okay, so I have a topological space, I have shards, and those shards are compatible if they don't intersect. In that case, I don't have nothing, but that's fine. But when they have points in common, these two functions must be smooth. Now, I'm going to define an atlas on a topological manifold M. So I'm going to have some shards. I don't know how many. It could be a finite number, uncountable, I don't know. But I'm going to require, the first thing is very trivial. All of the shards must cover M. So each point of M belongs to a shard. The second condition must be a strong condition. I will require that any two shards of the atlas are compatible. So that's going to be an atlas on a topological manifold. A collection of shards that cover the whole manifold, and the shards are compatible. And that's what I call an atlas. Y de nueva cuenta, atlas es la colección de mapas o de cartas en nuestro caso, ¿no? De ahí viene el nombre tal cual, lo mismo. Cartas, colección de cartas, un atlas. ¿Alguna pregunta hasta aquí?
Yo, profe, a poquito arriba, U y B son homeomorfos.
No. So, right. No, so U and V are shards only. And then, for this, I have U, V, shards. Because they are shards, they have these maps. But U and V, they have nothing in common. Only if they overlap, we require this. If they don't overlap, I don't care. No hay ninguna condición en U y V, son abiertos. Si no se intersectan, está bien, no pasa nada, son compatibles. Si se intersectan, nada más voy a pedir esta condición. Pero U y V no tienen por qué ser homeomorfos. En principio, U es una carta. Es un abierto y viene con un homeomorfismo a un abierto de Rn. Generalmente lo que vamos a dibujar es esto, pero por ejemplo U no tiene, por ejemplo, que ser conexo. Son cosas muy... no aportan nada para el conocimiento, ¿no? Pero es para responder tu pregunta de no hay ninguna limitante en U comparado con B. No son homeomorfos, no tienen nada en común. Tenemos X, espacio topológico, variedad topológica, y U y V son cartas. Eso es, vienen con un homeomorfismo, que le estoy llamando phi de U. El homeomorfismo nada más está definido en el abierto U. Y es un homeomorfismo hacia un abierto en Rn. Y lo mismo para B. B es otra carta. Es un abierto, tengo otra función y ya.
¿Cómo podemos asegurar entonces que los dos Rn son el mismo n?
Ah, exacto. Ahí estoy usando el hecho de que sí hay puntos en común.
Oh, ok.
Entonces, aquí tengo esto en común. Vamos a suponer que no sabemos que son iguales. ¿De acuerdo? No sabemos que son iguales. Muy bien. Entonces, nada más lo que estoy agarrando es que hay puntos en común. U intersección B, open. Son abiertos. Ahora, bajo la función, tengo este abierto aquí. Y bajo la función, distinto. No va a ser el mismo. Tengo otro abierto. So these are open. Son abiertos porque phi U y phi de B son continuas. La imagen de un abierto es un abierto. A lo mejor ahí quieres pensar en la otra función, pero por ser homeomorfismos, son funciones abiertas, mandan abiertos en abiertos. Para una función continua eso no es cierto, es una imagen de abiertos es abierta. Pero como phi U y phi B son homeomorfismos, mandan abiertos en abiertos. Entonces tengo esos dos conjuntos abiertos, aquí y aquí. Pero además tengo los homeomorfismos, que es el que se compone este de aquí. Composición de continuas es continua. Esa función es continua. ¿Y cómo sé que es un homeomorfismo? Porque la función de abajo es su inversa. Y el mismo argumento se aplica de que esa función de abajo es continua. Entonces, puede ser cualquiera, voy a escoger esta. Ese es un homeomorfismo entre abiertos de Rn. En este momento es cuando ya después invoco la observación. Y entonces n es igual a n.
Ok, gracias. Pensaba que era como de manera general.
Ajá. Entonces, U y B son cartas arbitrarias. Si no se intersectan, no hay problema, son compatibles. Cuando se intersectan, queremos que estas dos funciones definidas entre abiertos de Rn sean C infinito. Bien, realmente este es el adjetivo, el que sea infinito. Ahí ya pueden pedir ustedes lo que quieran. Si quieren hablar de análisis complejo, variable compleja, sean holomorfas. También han visto en análisis funciones analíticas, que son distintas a las suaves. Pueden pedir que esas funciones sean analíticas. Eso les da las distintas clases de variedades. Nosotros vamos a ver nada más suaves. Y voy a usar suave para decirle que son infinito. Y también cuando diga variedad, siempre se va a entender, si no digo más, una variedad suave o una variedad C infinito. Muy bien. Any more questions? Okay, so let's review what we have seen. I have a topological manifold, and then I fix, well, I say what it means for two shards to be compatible. And I require these two functions to be smooth. And then I have my topological manifold. I take some collection of shards. The only thing that I require is there must be enough of them so that I can cover M. So that would be even one shard, finite number, or many. But the actual condition that we require is that the shards of the atlas must be compatible. So let's see some examples. So this is the circle. This is a topological manifold of dimension 1. Okay? And I need to define some shards, see that they are compatible, and then check that I have an atlas. So I'm going to take these 4 shards. So UN stands for the north part. Okay? So basically, I'm just projecting. This is my function. Let's see. What is the image of 5n?
The open from -1 to 1.
Right. Okay. Now, notice that the reason that we remove the endpoints is to have an open set. U has to be open. So that's why we are neglecting the endpoints. In the same way, I have the south part, and I have that function. If we forget the compatible thing, we will look it up later. UN and US don't cover the circle. I'm missing 2 points. Right? So I'm missing this point and this one. So that's why I need more open sets. So I take the east and the west. And I define the functions the same way. So these are 4 shards of S1. The union of the U's covers S1. However, I must check that it is compatible. So let's check that 2 shards are compatible here. So what is the inverse of this function? So I name my x, and that's the one that I have to consider, right? So this is the inverse of 5n. So I'm looking at this and this. The inverse of U west, this one here. Okay? Now let's see that these 2 functions are compatible. So I have this. This is north and west. So the intersection is this quarter here. So that's why x is between -1 and 0, and the composition is this function. And there you have the inverse. And those 2 functions are smooth. You can take the derivative infinitely many times. So this and this, those 2 shards are compatible. Okay? Now, I only check these 2, but you can do it with the rest. So what you have is an atlas. Remember that with this 2 is not enough because we don't cover the whole circle. That's why we need the other 2 open sets. We just check that this is compatible, these 2, but any pair of shards that you take, they're going to be compatible. So you have an atlas on this one. Okay? Now, so this is an example of one atlas on the circle. We are going to see another one with fewer shards. At this point, do you have any questions? Okay. Let's move on. So the other one is something that you know very well, stereographic projection, right? So basically you remove one point and you have a homeomorphism to the real line. We will see that this will be an atlas with only 2 shards. So we are going to do stereographic projection from the North Pole and the South. right? So I take U to be the entire circle without the North Pole. And so this point is assigned this one under the projection. So all that you have to do is to compute the equation of the line. You have the points and then find when it crosses the x-axis. That will be the function phi of u. So this is the equation of the line that goes through this point and this point. And then you make y equals to 0, and you get the function phi of u. Note that there's trouble when y equals 1. At that point, it doesn't belong to u because we're removing this point. So this is a nice function, a homeomorphism. We have no trouble when y equals 1. The same reasoning will give you the other function. Now you project from the south pole 0, minus 1, compute the equation of the line, and set y equals to 0. And you get the other chart. Again here, the only trouble is when y equals minus 1, but that point is removed from the domain of the function. It's not on V. So these are the two charts. Okay? So you have the two charts on the sphere. They cover the whole, on the circle. U and V cover the whole circle. So in order to conclude that we have an atlas, we have to check that those two charts are compatible. So, and that will be a homework. Check that those two charts are compatible, and the conclusion will give you an atlas on S1. Okay? So that's homework number 1. Any questions? Okay, so in this way we have the circle and 2 atlases. This is the second one, U and V, and this one with 4 charts. Okay, good. Now, in order to make the exposition as clear as possible, I wrote down this example on S1. But you can do this with S2 or Sn. You have the same ideas, goes for the sphere of any dimension. Okay, so this was just examples. So let's move on. Let's work out a small proposition. So you have an atlas on a topological manifold X. And I have 2 charts that in principle, they don't have to belong to the atlas. And let's say if this chart is compatible with all of the atlases here, and this chart is compatible with all of the chart here, the conclusion is that these two are compatible. Okay? So this is what we're doing. So we want to show that U and V are compatible. So let's see, where are we going? We have the topological manifold X, and I have an atlas. So the whole idea is the atlas is going to have all the information to talk about smooth functions on X. Basically, we can do that. But we need to do a little bit of theory because, for instance, here I have two atlases on the circle. So we need to understand what's happening in terms of if I put more charts on my atlas, right? Entonces, para donde vamos es formalizar un poco el concepto del atlas. El atlas me va a ayudar a derivar, pero como vieron en el ejemplo del círculo, tenemos dos atlases en el círculo. Entonces, de cierta forma, son diferentes, son iguales, ¿qué podemos hacer? Eso por un lado. Por el otro lado, por toda la experiencia que ya tienen de cálculo, de topología inclusive, muchos de los argumentos que usaron para ver cualquier resultado, en un punto me tomo una vecindad. En ocasiones había la necesidad de tomarse vecindades más pequeñas o ir cambiando de vecindades del punto. ¿De acuerdo? En ese caso, pues como que este atlas no es tan agradable porque nomás tiene dos. Nada más son dos abiertos U y B. ¿Y qué tal si requieren por cualquier razón de análisis o de topología tener más abiertos y más pequeños? Entonces, esa es la necesidad de formalizar estos conceptos, de tener la variedad va a ser X con un atlas. Y la idea es tratar de decir que el atlas tiene toda la información. En términos teóricos, de que va a tener todos los abiertos que necesitan. ¿De acuerdo? Entonces, para allá vamos caminando para tener todos los abiertos posibles en el atlas. Muy bien. Ok. Entonces, so we want to show that U and V are compatible. If U and V don't have points in common, we are done. They are compatible. So the interesting thing is when U and V have points in common. Y también esta es la figura que vamos a estar usando muy a menudo. Y recuerden, arriba, cálculo de varias variables, y esa información la estamos trasladando abajo para poder derivar. Okay, so this is the picture that we have, and I want to show that this function defined on the appropriate small set, open set, is smooth. right? This is what I want to prove. Now, in order to prove that a function is smooth, we can do it also pointwise. Check that at any point in the domain, the function is smooth. And this is what we're going to do. So I'm going to take I want to prove that this is smooth. And for that, I'm going to take an arbitrary point here, x. This open set is where this function is defined, is this one, okay? So I want to show that this is smooth. I take an arbitrary point on the domain. I want to show that that function is smooth on x. Okay, so let's see. What happens to x? X is mapped here under this, okay? So I have it. This is this. And I have this point, that is this one. Right? Okay. And now here is where we use the hypothesis of the atlas. I have a point in x, but x has an atlas. The union of the u alphas cover x. So there must be some chart that contains that point. Because this is an atlas and covers x. Right? Okay. So here we are. Muy bien. So now, phi alpha, u alpha is from the atlas. I'm going to have a function here. What function is that? It's going to be phi Is that clear? And I'm going to have here also another function, which is okay. Now, remember what is the hypothesis on the atlas. The chart U is compatible with any chart of the atlas. The chart V is compatible with any chart of the atlas, right? So that means that these two functions are smooth. My hypothesis. Okay? So this and this are smooth by hypothesis. The composition of smooth functions is a smooth function. And the composition is exactly the function that I care about. So that shows that this function is smooth at x. And x was an arbitrary point on the domain. So the function is smooth. Similarly, for the other function, right? That goes on the other way. It is the same argument. Any question? Muy bien. A ver, ¿cuál es ahora la idea de este resultado? Yo ya tengo un atlas de que cubre a M, eso ya está cubierto. Lo que nos está diciendo es de que al atlas le puedes agregar más cartas que son compatibles. Y piénsenlo en la idea esta de que a lo mejor por decir, son U's pequeñitos que no tenían antes. Y les digo, por su experiencia en ocasiones requieren vecindades más pequeñas, qué sé yo. Entonces, la idea es nada más la compatibilidad, lo que nos interesa, porque ya estamos cubriendo a toda la variedad. Es un atlas, ya lo cubre. Pero por alguna razón tengo dos atlases, perdón, dos cartas que son compatibles con todas. Entonces los puedo anexar y generar un nuevo atlas. Va a tener dos elementos más. ¿De acuerdo? Porque ya sé que U es compatible con todas las cartas de A. B es compatible con todas las cartas de A también. Y además, ya sabemos que U y B son compatibles. Entonces, estoy generando un nuevo atlas, que es el anterior A, y le estoy agregando U y le estoy agregando B. Entonces, ese es el aspecto filosófico de esta proposición. Si ya tengo un atlas y me encuentro una carta compatible, las anexo. Las voy anexando. Muy bien. So, this is the next definition. A maximal atlas is an atlas that it is not contained in any other larger atlas. In other words, any chart that it is compatible with the chart of the atlas already belongs to the atlas. So the maximal atlas has all of the charts that you require. If you find some chart that it is already compatible with what you have, it's because it belongs to that atlas. Okay? And this is exactly what I said at the observation. If you find a chart that it is compatible, it belongs to the atlas. And that's what is a manifold. A manifold is a topological manifold of dimension n together with a maximal atlas A. Okay? So I think time has run out, so this is enough for today. But I just want to make a couple of comments. So let's see here. A ver, realmente lo que pasa en la práctica no hablas tal cual del atlas maximal. Por ejemplo, en R2, cuando vieron en R2 la topología de la métrica, tiene abiertos. Primero se pueden imaginar cualquier punto y todos los radios que quieran. Bestial, demasiados. Y esos no son todos, esos son como los bases, las bolitas con centro en X y radio R positivo. Y la colección de todos esos y sus uniones, esa es la topología estándar de R2. Pero realmente nunca les interesó describir todos los conjuntos de la topología. Con el concepto de una bola sale todo. Para una variedad es el espacio topológico, que es una variedad topológica X, y un atlas maximal. Esa es la teoría. El atlas tiene todas las cartas habidas y por haber, por así decirlo. Pero en la teoría ya no me interesa tener el atlas maximal. Nada más me va a interesar tener un atlas. Como los que vimos del círculo. Vimos un atlas con 4 abiertos y otro con 2. Con tener ese atlas me sirve para hacer todo lo de derivadas. Porque la idea es de que cualquier atlas va a estar contenido en un maximal. Entonces, no me voy a preocupar de qué tan grande es el atlas maximal ni nada. Teniendo un atlas, y como en estos casos, con un número finito de cartas, con eso podemos trabajar. Pero les digo, para que todo tenga consistencia y de que no se esté escapando nada, si es la idea de una variedad, tiene un atlas maximal, cosa que nunca vamos a ver tal cual, y es nada más para la teoría. Muy bien, ¿alguna pregunta?
No, creo que no.
Muy bien. Vamos a continuar mañana. Quiero de nuevo hacer énfasis en esta figura. Abajo tenemos la variedad topológica. Las flechas verticales son las cartas. Son funciones homeomorfas. O sea, que nada más pura topología. Pero para transitar de una carta a otra, es donde se involucran los conceptos de varias variables. En el concepto de cartas compatibles es donde entra ese concepto de diferenciación. Bien, y les digo, todo esto va a ser necesario, vamos a recurrir a ello. Como sucedió un momento, puse X espacio topológico. Nunca me interesó saber tau ni cómo era ni nada, nada más de que hay abiertos. Lo mismo va a pasar con una variedad. Tengo M una variedad. Nunca vamos a estar cargando con el Atlas, ¿de acuerdo? Entonces, obviamente apenas vamos empezando, iniciando conceptos, vamos a cargar toda la información de tenemos un Atlas, las cartas son compatibles, bla, bla, bla. Muy bien. Entonces, también recuerden algo muy importante. La carta, la phi, es como dar una parametrización local en X. Y ya después esa parametrización pues va a tener más sentido porque va a ser suave. Muy bien. Entonces llevan ahí los problemas de tarea, háganlos. Y continuamos mañana. ¿De acuerdo?
De acuerdo. Oye, profe, ¿va a subir estas notas ahí al Classroom?
Sí, sí, voy a subir las notas de todas las clases en el formato DF. Les digo, nada más, por ejemplo, hoy tengo que hacer algunos ajustes porque tengo todavía más cosas abajo, ¿no? Pero se van a compartir.
Okay.